Okay, this is the 13.5 video. This is actually take 3 of this video. So I'm super frustrated at this point. I'm going to try my best not to rush through it, but being as this is the 3rd time now I've done this, I'm making no promises. So if I seem a little speedy or more speedier, is that a word? Anyway, if I'm going faster than normal, it's, I'm sorry, let me apologize in advance, but again, 3rd time through for this video, so I'm getting really, really frustrated. But anyway, 13.5, directional derivatives and gradient vectors is what we're talking about. We're on page 723. So directional derivatives basically are just derivatives in a particular direction. They have a picture down here at the bottom of the page. Derivatives are the same thing as rate of change. So the rate of change, or the derivative of f in the direction of some unit vector u at some point p naught, is the rate at which the function is changing along this line that goes through p naught. So notice the line and the vector are parallel to each other. But again, the vector has to be a unit vector. That's why they use u, to remind you that it has to be a unit vector. So if you turn the page, you have the definition. This is at the top of page 724. This is the definition, but this is not what we're going to use for the computation. So when I ask you for a formula, this is not what I want. Okay, but here it's saying the derivative of f at some point in the direction of the unit vector u is, and then they give you this again for definition purposes, not computational purposes. But here, notice again, it has to be a unit vector. Unit vector, remember, is a vector that has length 1. So if it's not a unit vector, you can make it be a unit vector by dividing by its magnitude. This is one of the 2 notations for the directional derivative. Again, this is not the one we're going to use. And this is the limit definition. Again, not the one we're going to use, but this is what a directional derivative is. This is the notation that we're going to use here. This would go on the left side of the equal sign. And so it's capital D for derivative in the direction of u, where u is a unit vector, of the function f at the point p naught. So the derivative of f at p naught in the direction of u. So you've actually, you didn't know it, but you've actually already been computing directional derivatives. When you were doing the partial derivative with respect to x at a particular point, that was the directional derivative in the I direction. And then when you were doing the partial derivative with respect to y, that was the directional derivative in the j direction. So you've already been doing those. The I direction would be along the positive x-axis, and the j direction would be along the positive y-axis. But what we're going to look at in this section is how to do it in any direction. So it doesn't have to be along one of the axes. It can be in the direction of any vector, again, as long as that vector is a unit vector. So they talk down here at the bottom of the page that, and I have a good picture with it, the slope of a curve at some point p naught is just the directional derivative. And so the directional derivative is, again, the derivative, which one of the representations of derivatives is slopes of the tangent line or slopes of the curve. Okay, I'll let you read this later on your own, but on page 725 at the top, they give you a physical interpretation, kind of how you can think about where you would use directional derivatives. That's again at the top of page 725. But if you look down here, we're going to look at the gradient vector, because we need the gradient vector to do directional derivatives the way that we're going to do them. And so the gradient vector just basically is a vector that's made up of the partial derivatives. So if your function is a function of 2 variables, x and y, then the gradient vector would be the partial derivative with respect to x in the I direction, and the partial derivative with respect to y in the j direction. So again, it's just the vector that's made up of the partial derivatives. So if it's a function of 3 variables, it would just have an extra piece here, partial derivative with respect to z in the k direction. All right, so notice here, it's hard to tell, but this is, well, this is not what I want to tell you, but anyway, this is called del. It's del, but it's a vector. So you can't tell, but it's bold. Okay, so you can't tell that it's bold, but it's bold. So when you write it on your paper, this little upside down triangle, this del, it has to have a hat on it. If you don't put a hat on it, then it's not a vector, and then it's wrong. So make sure to put hats on top of the upside down triangle every time you write them for anything you're going to turn into me. Okay, and then if you take that gradient vector, that would be this vector here. This is the gradient vector at a point. If you take the gradient vector at the point and you do the dot product between that gradient vector and the u vector, where again u is a unit vector, then that dot product is the same thing as the directional derivative. So this is not what we want on the left side. What we want on the left side is this. So this is the notation that we're going to use for the directional derivative. For the left side of the equal sign, this is what goes on the right side of the equal sign. So I have it in my notes. I'll show you in just a second how you would actually, well, actually, I'll show it to you right now, how you actually write it. So in my notes, we have, just recapping what we've already talked about, the directional derivative. Here's the two notations for it. We are not going to use this one. We are going to use this one. But a couple of notes about this. Again, U must be a unit vector. Again, we've already been doing in the I and J direction. But here, this S, this is, again, for the one we're not going to use, but this S right there, just in case you were curious what that was. The S is just a parameter that has to do with arc length. But again, that's not the formula that we're, or the form that we're going to use, so don't worry about it. But just in case you were curious what the S was, that's it. Okay, and then again, talking about that this is the same as the slope of the curve at a particular direction. But here we go, at the bottom of my notes, here it's talking about, again, the gradient vector. And I'm going to show you, I didn't write it in here, but let me add it real quick. Hold on one second. This is a little bit easier way to write it. I wrote it in my notes later, but just while we have it here. The gradient vector, again, is the partial derivatives. But for partial derivatives, you can use the curly D notation like I have here, or you can use the subscript notation. So this is maybe more of a condensed way to write it. So if you want to write it this way, you can. But again, it's just a vector that's made up of all the partial derivatives. Okay, and then here, this is what we want. We're not going to use this one, so don't do that one. But this is what we want for the formula for the directional derivative. Okay, so we want the capital D notation and the dot product one. So not this and not the limit one. So this is what we want for directional derivative. And notice here the U is a vector, so it needs a hat. And the del is a vector, so it needs a hat. And the U. Okay, so let's look at some examples now. Oh, wait, hold on, just kidding. I got to show you something else first. Get ahead of myself here. Page 726, we're going to come back to this later, but go ahead and put a note in your notes or highlight it in your book that this is important. You're going to need this for one of the homework problems, but it's at the end of the section, and so we'll forget it by the time we get there. So I'm going to come back to this. But on page 727, they have some more information. Again, this is both information that's important to know and more formulas. But they talk about here the gradient vector is normal or orthogonal to the tangent vector. So it's normal to the curve. So here it talks about how, again, the same thing, the gradient vector is normal to the level curves through a particular point. So at a particular point, you have a specific level curve, and then the gradient vector would be normal or orthogonal to that, that level curve. So there's a picture of it here. So you have a specific level curve here at a particular point, and then this is the gradient vector normal to that level curve. Okay, and then here at the bottom of the page, this up here that it's talking about with these streams flowing perpendicular, blah, 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 they were talking about that up here at this paragraph. So if you want this to make sense, you'd have to have read this paragraph at the top of 723 first, and then this is a continuation of that. But what we care about is this down here. And we have done tangent lines before, but when we did tangent lines, we used the parametric equations for the tangent lines. So this is another tangent line formula that we couldn't do before because before we didn't know how to do partial derivatives. But now that we know how to do partial derivatives, we can use this form for the tangent line. So it's a little bit better than the parametric equations because it looks more like the tangent line equations that you would have done in algebra. So it's a little bit easier to graph, I think. But here, this one at the bottom is the one that we're going to use. This would be the equation for the tangent line. The partial derivatives are like the slopes, right? We were talking about a minute ago how the slope of the curve, which is the same thing as the slope of the tangent line, is given by these derivatives, and so that's what we have here. So we have basically slope times this and slope times this, depending on the direction that we're going. So the I direction or the J direction, respectively. Okay, so now they have a couple more things here. Some algebra rules on page 728. And then down here for functions of 3 variables, the same formulas, but for functions of 3 variables. So notice here x, y, z. So the gradient vector has an extra component, and so you do the dot product, an extra piece. But same principle, just more pieces. All right, now let's look at some examples. 1 through 6, you want to find the gradient vector, and then you want to sketch the level curve and the gradient vector to that level curve. So we're going to do number 2. So here's number 2. You have a function and a point. So you're going to start by finding the gradient vector, which again, the gradient vector is the vector that's made up of the partial derivative. So you've got to find the partial derivative. So you can use the curly D notation or the subscript notation, doesn't matter to me. I think I start off using the curly D notation and then later I get tired of it and start using the subscript notation, but either one's fine. All right, so partial derivative with respect to x, then the partial derivative with respect to y. So you can do this one of two ways this next step. This is what I start doing, and then I kind of change it later. But I write first the gradient vector as a function of x and y, and then I plug my point into it. But I think what the book does is after they find these partial derivatives up here, they plug the point in, and then they write it as a vector. It doesn't matter what order you do it in, so whichever way you want to do it is fine. But I write my gradient vector as a vector, then I plug in my point. So notice it's still a vector. The gradient vector is a vector, so it should still be a vector. So it's the vector I plus j, so 1, 1 as a vector. Coincidentally the same as a point, but not same as this point, but not true in general. So don't assume that the point and the vector are going to be the same thing, because that's not true in general. Okay, so now for the level curve. For the level curve, the f of xy is the z. Level curves are when you take c's and plug different c values in for the z to get graphs in the xy plane. So the level curves are graphs in the xy plane. So you want to figure out which c value corresponds to this point. Okay, so if you plug that point into the original function, notice into the f. Okay, so plug it into the f. So up here at the top, the original, you're plugging in the point, and so that gives you ln of 2. So the z value, or c, the c is a specific z value, or for a number, right? Z is a variable, c is a number. So this one is ln of 2. So if you take the ln of 2, that's going to be this f of x, y, or z, and then you set it equal to this. So you have, you're going to let f of x, y equal ln of 2, but from up here, you also know that ln of x, y, sorry, f of x, y is ln of x squared plus y squared. So if you set those two equal to each other, if f of x equals this and f of x equals this, then they have to be equal to each other. You get this. And now you can solve this. Since there's ln's on both sides, you can take the e of both sides. So if you take the e of both sides, the e and the ln cancel each other out. So you have 2 equals x squared plus y squared. So that's obviously a circle centered at the origin, radius square root of 2. So I've graphed the circle here. Then for the gradient vector, if you go back up here, I don't really have it written very well, but the gradient vector at the point 1, 1 equals this vector I plus j. So this point is where it starts. So you're going to start at 1, 1. That point should be on the curve. Okay, so if it's not, you did something wrong. Start there, and then this tells you how to move. So start at 1, 1. See how I'm at 1, 1, and I start there on the curve, and then I move 1 to the right and up 1, and then that's my vector. So that's my gradient vector. Okay, so the starting point is the point, and then the vector tells you how to move. All right. And I'll write that down here in words if that's easier. So gradient vector starts at 1, 1 and moves 1 in the I and 1 in the j. All right, so let's look at the next group of problems. 7 through 10, it just wants the gradient vector at the particular point. So all we're doing is the gradient vector. So we're doing number 8. Let's get it closer. All right, so here's my function. My point is 1, 1, 1. So I need to start by finding my gradient vector as a function. So I'm going to start with the individual partial derivatives. So here's timeout. Hold on. Here's what I would recommend, because you should already, you've done 2 sections now worth of partial derivatives. You should be feeling good about partial derivatives. So here's what I want you to do. Pause the video and do the 3 partial derivatives on your own, and then start it up again and check them. Okay, so pause the video, do the partial derivatives, and then come back. Okay, so hopefully by now you've already done the partial derivatives, so you can check your answers. That's kind of messy, but here they are individually. Here's the partial with respect to x. Here's the partial with respect to y. And this one's really long. This one is the partial with respect to z. So I wrote it down here as a vector. You've got partial with respect to x here, partial with respect to y here, partial with respect to z here. So hopefully you got all those right. Now we're going to plug in the point. So we're plugging in 1, 1, 1. And after a lot of simplification, you get down to here. Okay, so this is the gradient vector at that point. So it would be, again, the vector that's made up of all of the partial derivatives, but then you plug in the point. All right, so that's all for number 8. Now we finally get to do some actual directional derivatives in 11 to 18. So 11 to 18, it says find the derivative of the function in the direction of u. Notice here the wording find the derivative in the direction of, that's the same thing as find the directional derivative. It's just a different way to word it. Okay, so that's what we're doing. So we're going to do number 18. Number 18, they give you the function and they give you the point. And so again, we need, they also, sorry, I forgot about this. They also give you a vector. But for directional derivatives, remember the vector has to be a unit vector, which means it has a magnitude of 1. This does not have a magnitude of 1, so you have to fix it. So here's what I would recommend is fix it first so that you don't forget. So I go ahead and fix it right now. So I want to make this be a unit vector, so I'm going to divide by its magnitude. So the magnitude is 3. So divide the magnitude by 3. And so this is the vector that I'm going to use, not this one. So don't use this. Use this, because again, it has to be a unit vector. If it's not a unit vector, it's going to be the wrong answer every time. Okay, so we're going to use that as our u vector. Okay, now we need to find the gradient. Here I've switched to started using the subscript notation instead of the curly D's. Again, it doesn't matter which one you do. Now I've gone back to the curly D's here. So we're finding the partial derivatives. Again, if you want to practice with your partial derivatives, pause the video, find the 3 partial derivatives, then come back and check your answers. So we have the partial with respect to x. This would be the simplified version here. And then on the next page, the partial with respect to y. There's the work and the simplified answer. And then the partial with respect to z, the work and the simplified answer. So as a gradient vector, as a function of x, y, and z, doesn't all fit on one line, but there it is. Now we're going to plug in the point. So the point was 1, 0, 1/2. So you're plugging that in. Again, it didn't all fit on one line. Lots of simplification. And you get down to 1, 1/2, 2. So 1, 1/2, 2, that's the gradient vector. And then you're going to do to get the directional derivative, you're going to do the dot product of the gradient vector with the vector that is giving you direction, but again, as a unit vector. So here we have the gradient vector and then the u as a unit vector. So here's my gradient vector. Here's my u that I changed to be a unit vector. I'm going to do the dot product between these. And so I get 2. So notice that because directional derivatives are dot products and dot products are scalars, directional derivatives are scalars. So gradient vectors are vectors, but directional derivatives are scalars. So for your final answer for a directional derivative, it should not be a vector. Okay, it should just be a scalar. Okay, let's look at the next group of problems. So turn the page. 19 to 24. It says find the directions in which the functions increase and decrease most rapidly at p0, and then find the derivatives in these directions. This is where we need that box I was talking about. So flip back to page 726. And if you look at number 1 and 2, number 1 says I'm going to kind of skip around a little bit, but the function increases most rapidly, skipping down, in the direction of the gradient vector. So increases in the direction of the gradient vector. And then in number 2, it decreases most rapidly in the direction of negative here, so the opposite direction of the gradient vector. So if you go in the direction of the gradient vector, that's where it's increasing most rapidly. If you go in the opposite direction of the gradient vector, that's where it's decreasing most rapidly. So it all boils down to the gradient vector, which means we've got to find the gradient vector. So we're doing 22. Again, all that stuff I just read was on page 726. So we have to start with finding the gradient vector. So I have here my 3 partial derivatives, and then I'll put that together to make a vector. So the gradient vector as a function of x, y, and z is here. Then I want to plug in my point. Okay, so if I plug in my point and simplify, and I put a little dot by this so I could find it later when I need it. But this is my gradient vector. But before I keep going, let me just warn you. If I asked you which direction does it increase most rapidly and you told me this, it would be wrong. See if you can think why. So I'm going to pause it, or I'll wait just a second. But why would this be wrong for the direction? All right, so hopefully you've thought about this. And I don't know how many times I've said it, but hopefully enough times that you remember, whenever you talk about direction, you have to give direction as a unit vector. So direction has to be as a unit vector. Now this vector is the direction that I want to go, but it's not a unit vector, so I can't use it as my answer. So If you look at it like, here's kind of the idea. So if I want to go in this direction, then the unit vector and the vector, see, they're going the same way, but whenever you give an answer in terms of direction, it would have to be a unit vector, not the vector itself. Okay, so here's the vector itself. Now we have to make it be a unit vector. So we're going to compute the magnitude and then divide the vector by its magnitude. And so now this, again, same direction as the other vector, but it's a unit vector. So that's what I'm going to use. And so G increases most rapidly in the direction of this vector. So anytime you are giving me an answer for direction, it has to be a unit vector. Okay, so this would be where it's increasing most rapidly. Now it decreases most rapidly in the opposite direction. So all you have to do is scalar multiplication, multiply by a -1. So you're just changing every sign. And if all you did was change the signs, it's still a unit vector. So you just made it go, like here, for instance. This is, say this is the unit vector. You just made it go this way. Well, pretend like those are parallel. They're not really parallel there, but pretend like they're parallel. Then same, it's still a unit vector, just opposite direction. Okay. Okay. So now it wants the directional derivative in those directions. Okay, so the directional derivative in the direction of u, I've taken my gradient vector and my u vector. Wait, hold on. Yeah, okay, sorry, just kidding. I thought I did something wrong. I got it there. Okay, so here you have your gradient vector. I thought I was using something else, but I'm not, so I'm good. I thought I was doing something wrong, but for once I am not. So this is my gradient vector. This is my u vector. I'm going to show you a little, okay, don't look at my note out to the side. You can totally do it this way, and this makes sense because this is the way for the definition. There's a faster way to do this. I'll show you in just a minute. All right, so notice this is the gradient vector. This is the vector that's giving me the direction, which came from here, the direction in which it increases most rapidly. That's where I got that from. All right, so I'm going to do the dot product between those two, and I get 3, which I don't know if you noticed this, but magically, this is not a coincidence. See how 3 was the magnitude of the gradient vector? That's going to always be that way in these problems. If you have done the gradient vector, and then you have found this was the direction of the gradient vector, right? This was the gradient vector as a unit vector. So if you take a vector times the unit vector in the same direction, it's always just going to, when it's a dot product, it's always just going to give you the magnitude of that vector. So this was the gradient vector. This was the magnitude of the gradient vector. It's just going to give you, I'm sorry, I said that wrong. Time out. Let's do that again. This is the gradient vector. This is the gradient vector as a unit vector. So if you do the dot product between the gradient vector and the gradient vector as a unit vector, it's just going to give you the magnitude of the gradient vector. That happens that way every time. So if you forget that, you can do the dot product and you'll get that. Or if you remember it, it's a little faster because you've already found that number up here and you can just reuse it. So, okay, and then for the other one, the directional derivative in the direction where it's decreasing most rapidly, it's just the negative of that. So it's, if you look at it, hold on. If you look at it here, all you would be doing would be using this vector instead. And so see how every one of these signs would be the opposite. So it would just make this be the opposite. So instead of redoing that every time, you can just do the negative of the answer that you just got, and it's a lot faster. Okay, lastly, 25 to 28, it says sketch the curve together with the gradient vector and the tangent line, then write the equation for the tangent line. So the equation for the tangent line was on page 727, and this box right above example 4. So that's where I'm getting that from, 727, box above example 4. But we are going to do 26. So notice if you graph this, to graph it you want to solve for y because that's easier. So solving for y, you get y equals x squared minus 1, which is just a parabola shifted down 1 unit. So it would be this, the parabola shifted down 1 unit. And then in the problem it said that you have f of xy equals c. And so if this equals 1, then this would be the f of xy and this is the c. So f of xy is this, c equals this. You don't really care about the c. The c was just giving you a particular level curve. So this is a particular level curve of some other function, but it doesn't play a role in what we're doing right here, so don't worry about it. Okay, so for the tangent line, you need the partial derivatives. So this is my function, x squared minus y. I have the partial derivative with respect to x, partial derivative with respect to y. So my gradient vector here is 2x in the I minus j. Plug in my point, and then this is my gradient vector. So to graph that, I start here at the square root of 2, 1. So that's my starting point. So c square root of 2, 1, that's where I start. And then this tells me how to move. So 2 square roots of 2, square root of 2 is about 1.4. So 2 square roots of 2 is about 2.8. So you're going to move 2.8 this way, and then 1 this way, and that's going to be your gradient vector. So now we need the tangent line. I haven't told you any stories for this. Let's think. What story can I tell you? I got nothing. Well, yesterday was Father's Day, so I got to see my son because he came over to see my husband for Father's Day because he doesn't live here, and found out my son is moving to Arizona in 2 weeks, which is kind of sad because Arizona, Alabama, really far apart. So that's very sad, but I guess he's about to be 22, so I guess he just feels like he needs to get away. I don't know. Who knows? But anyway, so that's kind of sad, but it is what it is. Maybe he'll come back. So if you don't live near your parents, probably your mother misses you terribly. Please take a moment to call her and tell her how much you love her and how desperately you miss her, because I'm sure she misses you too. So hopefully my son will call me regularly to tell me how much he desperately misses me. I doubt it. Whatever. Tangent lines. Page 727. Didn't we just talk about this? Yes. Here is the formula. We just haven't done it yet, but there's the formula. So I wrote it here for easier reference. We already found this value and this value. That was these numbers up here. The x naught, y naught is this point up here that they gave us. So we just plug it in. Oh, the sun, it just got dark all of a sudden. The sun must have gone behind a cloud. Felt like somebody turned out the light. Okay, anyway, it's all right. So here's my values. I plug it all into my equation. Simplify completely always, please. And then normally, let me just say this. Normally, for my answer, so going to here, normally I would have just moved that 3 over to here and had 2 times square root of 2x minus y equals 3. That's normally what I would have done. But since it asked me to graph it, I have to graph the tangent line. So to graph it, it's easier to solve it for y. So that's why I solved it for y here, and I don't normally do that. That's because I have to graph it. So this is a line. It has a slope of roughly 2.8 and a y-intercept of -3, but I don't really care about that so much as what it looks like at the point of tangency. So here's the point of tangency, and then I drew my tangent line. So notice if I kept it coming down, the y-intercept would be -3, but that would be way down here, so I can't fit it. But that would be the tangent line. So the tangent line, of course, is tangent to the curve, and then the gradient vector is normal to the curve, or orthogonal to the curve. So that's what it looks like graphically. Okay, so that is, for the third time, the end of my 13.3 note. Sorry, just kidding, 13.5 notes, 13.5. So if you have any questions, just send me an email.